It's an honor to give a talk here at IAS. Yes, this work is joint work with Andrew, who is here, so you can ask him about some details which I will omit, maybe. Okay, so the equation I'm going to talk about is wave maps equation from the Riemannian plane, the Minkowski plane, sorry, R1 plus 2 two-dimensional Minkowski plane to a Riemannian manifold N, which is a natural generalization of the linear wave equation with values in a manifold. Okay, so instead of requiring the D'Alembert equal to 0, we require that it is orthogonal to the tangent plane at a given point. I will restrict only to the very special case, to the Riemannian manifold being the two-dimensional sphere. And moreover, even this special case is very hard to analyze, so I will make a further restriction, only requiring, I will only consider symmetric solutions, which are called k-equivariant solutions. So the maps are from the plane for fixed t. This is a map from the plane to the sphere, which means a unit vector at each point. So here this equivariant reduction means that when we follow the half line, let's say of positive x0, then the values are on the meridian, the zero meridian of the sphere, and this is the u gives the coaltitude. Okay. And then when we make a turn on the argument side, we make k turns on the value side on the sphere.
Can you draw a picture?
Yes, yes. I'm very bad at drawing 3D pictures. I wanted to avoid this, but okay. Okay, so we have a plane. And usually there can be any vector on any unit vector at each point. And here we assume that when we move along this axis on the sphere, this would map to a meridian somehow. So this point maps to the South Pole, let's say, and then we follow one of the meridians, and u is the angle, the coaltitude, so this angle is u at each point. I don't know if this is very helpful.
So you have some kind of equivariant map into the sphere, right? And so everything, once you've written in that form, that form already takes values in the sphere. I guess that's all.
Yes.
So,
yeah.
So then it just reduces. You don't have any other constraints once you've got that equation. So everything's built already in that equation you're following, wave map. Right?
Yes, exactly. So
I don't have any further constraints to be concerned about.
No. I'm just assuming that at each time I have this kind of map, and then being a solution of the wave map equation exactly means that u is a solution of this system. This is equivalent. Okay, so I call this system this equation the wave map equation, and I will look at this as a Hamiltonian equation in the phase space, which are pairs of functions. Okay, so this equation has a natural energy. I wrote it here. This is the energy of this this nonlinear wave equation. And then I want to consider this in a functional space which I call the energy space, which is the H cross L2. And this is because the energy norm is the easiest to control, because we have this energy, which is a conserved quantity. And at some point we might want to pass to a limit. So that's why it's convenient to take this as a phase space. So this is the functional space of more or less of functions of finite energy, with one restriction which I will explain in a moment. And this is a notation. So I will denote H, which is the norm of this potential part of the potential energy, and L2, the kinetic energy, is just L2 square. Okay, and with bold phase I will denote pairs of functions. So bold phase letters will be elements of the phase space here. All right?
what's it? How are you distinguishing V from U? Oh, no. What is it?
I know V, I noted V because the V is an element of the phase space and the U is evolution. It's a function from T to the phase space. So that's why I use a different letter here. So for each element of the phase space V, I have the energy, which is defined like this.
Should that be U dot or that same thing?
You can put U there for the solution. The solution will have the property that the energy is constant.
Yeah, I understand that.
E of U. So that is, so you're right. You can put U there.
Okay.
Just didn't want to confuse notation.
All right.
Yeah. So because V is like the fixed frame for fixed time, the element of the phase space, and for U, I wanted to reserve for evolution of the. So a function from time to the phase space. All right. So I said that E is energy space, which is a functional space of pairs of functions of finite energy, with the restriction that they have zero limit at the same limit. So the limit is zero both at r equal to 0 and r equal to infinity, because the functions. So if you want the energy to be finite, this has to start at the pole and finish at the pole at infinity, but it can do some number of turns around the sphere, and we don't want this. So we want the evolution to start at the North Pole and finish again at the North Pole. So the elements which we allow of the phase space look like this. No, this is U or R. Okay, so now I only use the letter U for these functions. So a function which looks like this, which started at 0 and then approaches, let's say 2 pi or pi. It could also have finite energy, but we don't allow. I will not allow such functions here. So I want always functions to converge to 0 at infinity, which is implicitly contained in the definition of E. So the pairs of functions which belong to E have to satisfy this.
What does this mean geometrically for the degree of the map?
So for the degree, it's a bit more delicate. I will come back to this. So this implies that the degree is equal to 0, but it is not equivalent. Okay. So we can, when we want to, I said that because of some need of a limit passage, we want to consider the flow in the energy space. We need some local well-posedness theory in this space, and it can be established. This is quite by some classical arguments. So these works are not exactly for this equation, but the same arguments work to give some notion of solution such that we have local well-posedness, so local solutions which are continuous from time to the energy space for each initial data. So there is some notion of solution which makes this true, and which also such that also the solutions satisfy the conservation of energy. Okay. So this is more or less for any this kind of wave equation. This would be true. What is specific about this equation is the scaling property. So here, okay, again I'm using this letter V for an element of the phase space, but now it's clear. So for each element of the phase space, I can consider this rescaled version of V for any lambda positive. So here what it means is that for small lambda is a characteristic length here. So if we think of V as being a fixed function, then if I take lambda small, this means that I'm zooming at a very small scale. And that's it. And this is also an element of the energy of the phase space. Okay, and what is curious about this, special about this equation is that the energy, when we compute the energy, we get the same value. So this scaling does not change the energy. This rescaling does not change the energy. Does not change the energy norm either. So the energy norm is the same. The energy is the same. And moreover, we obtain a solution. So if U of t, if we get a solution of the wave map equation, we can rescale both space and time. So if for each time we rescale, so we look, let's say, at small scales for lambda small, And we also obtain a solution provided that we also rescale the time.
How are 3 dimensions different than this? What happens in 3 dimensions?
In 3 dimensions is supercritical. So for small lambda, we get a smaller and smaller energy.
Can you explain why you look at 2D, not 3D?
So this is because this is the critical so this means that with respect to energy, this is a critical problem. So if we assume boundedness of the energy norm, which we can assume, it suffices to assume that the initial data has bounded energy, then by conservation of energy we have boundedness of the energy norm. Then by looking at small scales, this assumption is not improved. So at small scales, if we assume that the solution has bounded energy norm, when we look at the small scale, then this is exactly the same information. We have boundedness of the energy norm and not smallness of the energy norm. So in this sense, this is a critical problem for the energy norm. And the energy is the only conservation law we know. So this is that's why we call it a critical problem here in this case. So for in 1D, this would be a subcritical problem. So this means that if we assume boundedness of energy and then we look at the small scale, we get smallness of energy at a small scale. So this is a subcritical problem. In 3D, when we assume boundedness of energy, we look at the small scale, we don't get anything. So this is a supercritical. In 3D and more D, this would be a supercritical problem. All right. Okay, this equation has stationary states, which are explicit and well known. These are classical, they are called harmonic maps from the plane to the sphere, so were studied in geometry. So in general, they correspond to rational maps from the sphere to the sphere, and Riemann sphere to the Riemann sphere. So meromorphic maps from the Riemann sphere to itself, and after the graphic projection, we get stationary solutions. Here they are explicit because I'm only looking at these equivariant maps, and they can be written like this: 2 arctangent of r power k over lambda power k. Okay, and these are all the equivariant ones. And energy is 4 k pi. This energy in general is related to the topological degree. So Wilhelm mentioned the topological degree. And so this is because they have degree k, and the energy will always be 4 pi times the degree of the map. And yes, what I wanted to say. No, for now that's all. Okay, and these are somehow what are called the ground states because they are threshold elements for nonlinear behavior, as was shown in a paper of Andrew Wilhelm with co-authors. So the result is the following: that if U0 has energy strictly smaller than the energy of the stationary solution, the ground state, then the solution exists for all times and scatters in both time directions. So yes, so I think I cannot say anything more about this. This was proved for some more regular solutions by Sterbens and Tataru in the non-equivariant setting. Okay, but here the point is that, so this is an optimal result, of course, because if we allow, so here the assumption is energy strictly smaller than 4k pi. There exists a solution of energy exactly 4k pi, which does not scatter, and this is Q. So this is an optimal result, but in some sense it is not really optimal because a scattering solution has to, let's say, I haven't defined what it means exactly, but let's say that at least it tends to 0 in the L infinity norm, which means it's contractible, so it has to have topological degree 0, and these solutions Q do not have topological degree 0. So one might ask, what would be the threshold? Is it really 4k pi, or maybe if we assume that U0 has topological degree 0, because we know that it has to have topological degree 0 if you want the solution to scatter, then maybe this threshold is different because Q is not a witness for optimality anymore in this setting. So they proved that indeed this threshold changes it was in the same paper, in fact, I think. right? Yes. That if U0 satisfies this condition that limit at 0 is equal to the limit at infinity, and the energy is smaller than 8 k-pi, so twice as much as before, then the solution exists globally, scatters in both time directions. So here I come back to this, what Wilhelm mentioned, that relation with the topological degree. So if we assume that energy is smaller or equal to 8 k-pi, then this assumption here is equivalent to the assumption of the topological degree being 0. But for arbitrary energies, this is not the case. So the equivariant maps have always topological degree 0 or k. So if you go, this is 0, then if you go to 2 pi, this will be k. If we go up again, this will be again 0, and then k, and 0, and k, etc. But in this, with this additional assumption that energy is at most 8 k-pi, this is equivalent. Okay, so in this sense, this follows this intuition that we need topology to be trivial, and with trivial topology we cannot have a non-scattering solution of energy for k-pi.
Could you before you go on, could you remind us what I believe there are blow-up solutions to these things which were discovered by Chatal and others? Is that correct?
They were constructed by. Yes, yes. Here, yeah, they were constructed by.
3 dimensions is Chatal. That's the super critical case.
Okay. Okay.
So maybe Jacek will explain construction of blow-up solutions for your case, for the critical case.
So I will just mention. I'm mentioning it here. So this result is in some sense optimal, because there exist solutions which have energy so bigger than 8 k-pi, but as close to 8 k-pi as we want, and which do not scatter because they blow up. And the reason for this is that there are solutions which have topological degree k and energy slightly larger than 4 k-pi, which blow up. And then by finite speed of propagation, we can attach whatever we want later once the solution blows up, so we can go back to 0 with energy 4 k as close to 4 k-pi as we want. And that's how we can obtain solutions.
So this shows there are blow-up solutions.
There are blow-up solutions for this equation. Yes, yes, yes. Mm-hmm. Okay, so in this.
And you understand the nature of this blow-up? I mean, so do you know what the blow-ups look like, or?
No, there are. No, there is no classification. So there are constructions of stable blow-up solutions in some topology by Sterbens and Rodniański, and then Rodniański and Raphael in some topology, but there is not really any classification in any topology for blow-up solutions. But there are also solutions which are kind of exotic, by Krieger, Schlag, and Tataru. Krieger, Schlag, and Tataru, which have different dynamical behavior than these stable blow-up solutions. So this it seems to be complicated to classify, but I don't think there is any classification. There are recent results by Krieger, but it is for 3D. It's not for the wave matrix equation. So the only classification which is known is the result of that they have to debubbling. They have to decompose into harmonic maps at different scales for a sequence of times. So this is works of Struve, and then it was a bit strengthened by Kott. Okay. So in this sense, this is an optimal result. This threshold is optimal, but the case of exactly 8 k-pi, so the threshold case is open. So here we don't know. And this is what I would like to describe here. Okay, so here we have these two theorems are instances of an attempt to solve the soliton resolution conjecture. Because the soliton resolution theorem would imply both these results quite easily, but here we have weaker results. But okay, I don't want to talk too much about soliton resolution conjecture here. Okay, so I'm considering solutions which have exactly this threshold energy 8 k-pi here, and I want to understand what can happen at exactly this energy. So I proved that there are blow-ups. There are non-scattering solutions which have exactly this energy. So we don't need this eta here. This is not needed. We can take exactly equal. So not blow up in finite time, but at least which do not scatter. So this is truly an optimal assumption. So we cannot replace strict inequality here by non-strict inequality. At least for k bigger than 3. But it is expected also for k2 and 1 to be the same. So the result is that there exists a solution of the wave map system which asymptotically as time goes to minus infinity decomposes as a superposition of two stationary states, one of which has a fixed scale and the other one is concentrating. So here I can draw it.
In this theorem, you're assuming it's 8 pi k or what?
This follows from this formula because here this scale goes to 0. So they decouple, the cross terms tend to 0. So energy of this thing is 4k pi. This is also 4k pi. The cross terms go to 0. So the energy of this by conservation of energy has to be equal to 8k pi.
So it is.
Yes, it's exactly equal to 8k pi. So these solutions, as time goes to minus infinity for so a concentrated bubble looks like this, goes to from 0 to pi, and then back to 0 at a fixed scale. So here this is my scale t power minus 2 over k minus 2, and the characteristic scale here would be 1. Okay, so this is at time t, it looks like this, and then as time goes to infinity, this first part becomes more and more concentrated, and the second part is always the same scale, 1. And as time goes to infinity, this scale tends to 0 here. This is how these solutions behave. Okay, so this is not so relevant, but here the related works. So here the crucial phenomenon is a concentration of this second bubble, and this was studied a lot. And I mentioned already these works of Kriegerschak and Tataru, which were extended in various ways later, of constructions of blow-up solutions and of stable blow-up by Raffaele and Rudniański. Sorry, I should mention also Stermans and Rudniański. Yes, okay, so this is a remark which this word is not really well chosen, so let me try to explain it in another way. So strong, but strong interaction of bubbles, I'm convinced that this is what we should call a strong interaction of bubbles. And what I mean...
Yeah, those are two bubbles there, are they? I mean,
these are two, so this is... They are called... Okay, so maybe some people don't like to call a bubble something which does not concentrate, but let me call it a bubble, okay? So for me a bubble is any instance of a stationary state, at any scale.
Yeah.
Okay, so both of them I will call bubbles. So in this sense, there are two bubbles here. And I'm claiming that I should call this as that they interact strongly because the dynamics is affected at first at the main order of this bubble. So because a bubble, when we don't add anything to a bubble, it's just stationary, it does not change scale in itself. So here the interaction between the two is crucial so that it can concentrate. So it's not like multi-solitons. So usual multi-solitons move in different directions, so with different speeds, but each one of them would move in itself without interacting with the others. So here it's not the case. It would not move in the same, but I wrote here pushed by the first one. It's not really correct as we will see a bit later. I should say dragged by the first one probably because I think the correct physical intuition here is that we look at towards the negative times, and this first bubble has some moment at any given time. So some speed going in this direction. Like when we think of the Newton equation, we can think of the two-body problem as an analogy. This is just to have an intuition of a large mass here and the point mass going in this direction. So we should throw this with some velocity in this direction, and then at infinity it will start slowing down, but it will, if it has exactly the escape velocity, then it will continue moving to infinity. And this is how we can think. This is, in my opinion, the correct physical intuition. The correct intuition is this. So this has some velocity at any given time, and then this velocity is smaller and smaller, but it can be chosen such that this dynamics continues to infinity. Okay, so this is how the interaction happens here. So the interaction between these two bubbles is attractive. That's why the word pushed is not the right one, because pushed would suggest a repulsive interaction. This is not the case. This is an attractive interaction here. Okay, and the second result.
Sorry, can you go back?
Yes.
What's in these two papers by Martel, Raphael, and Wien? What is that?
Ah, yes. So Martel and Raphael, these are papers where you also have strong interactions of solitons.
Which equation?
For the NLS equation in the Martel and Raphael L2 critical NLS equation. So this is a case of blowing up bubbles which blow up at the same
L2 critical in which dimension?
in dimension 2.
Cubic, and they look at two ground states?
Any number which are on a regular polygon, and they blow up at the same point, like the explicit blow up rate, but modified by the interaction.
So non-radial? Yeah, so that.
No. Yes.
And what is
Wien is the KdV equation. So he constructed multi-solitons which have asymptotically the same speed. And the physical intuition is the same, that you get the first one goes slightly faster than the second one, but he is attracted by the first one, so asymptotically they continue moving apart, but asymptotically the speed becomes the same
so the
at infinity.
is always equal to the sum of the energies of the solitons in these constructions?
So here and here, yes, but here, okay, I understand more what is happening here. Here I understand a bit less, but this is energy is the same as the sum of energies. Here it's also the same as the sum of energies. But I don't know if it's the right indicator, because sum of energies, I mean, for a linear equation, it's not the energy of the superposition, it's not the sum of energies. Asymptotically, you have decoupling, but no, so you don't have decoupling. So here, even though the energy is equal to the sum of energies, they don't decouple. They continue interacting, and at main order you see the interaction.
Does the leading one sort of pull the other one with it slightly?
Attracting. They attract.
Yeah.
Yes. So for in the repulsive case.
But this is not repulsive, or is it?
No. Everything is attractive here. You need attraction to have this kind of construction. Yes. Repulsion creates some dispersion always. It's not proved, but this is what it seems to be true. All right, so it's okay. So this was the first result about construction. Now, a second result with ND is that we can classify any. We can say what is a dynamic. What can be the dynamical behavior of any solution of this energy, 8k pi. And there are essentially two possibilities. Of course, we can have scattering. This would be a typical solution with scatter. But we know that there are solutions which don't scatter, because we saw in the previous theorem. But we can say what exactly they have. Any such solution has to have a specific behavior. And this is exactly the behavior which we saw. So if it does not scatter, then what happens is that it scatters in one time direction, and the other time direction we have exactly this behavior, decomposition into two bubbles for continuous time, and one bubble converges to some fixed scale, some number between 0 and plus infinity, and the other one converges to 0 at a specific rate which we determine.
Okay, can you say something why you have minus q plus q?
This is the attractive case.
So you show that you can't have plus q, or
well, in the radial case, this is impossible, because any such solution would have energy strictly larger than 8k pi. And in the non-equivariant case, this is, don't know.
Can you go back so that we can see the less than 8 pi k theorem? So can you remind everybody what's the less? So this is an extremely remarkable theorem. So yeah, that
Here, yes.
this is less than 8 k pi.
Less.
And you always globally scatter the statement.
Yes, this is a statement of their theorem.
So,
And here we have this threshold case.
You're at the threshold, and now you have an alternative. Right?
Alternative, yes.
You either scatter or you form this combination of. But this is a combination in which the ut is it becoming sharper or under the scaling? What's happening?
Here, this is exactly this behavior. So one of the bubbles converges, the scale converges to some number, because okay, in this theorem, of course, we could rescale everything, and obtain, instead of q, we could obtain q mu naught for some any mu naught.
I'm just confused about the parameters. So are we getting something that looks sharper and sharper or not?
Yes.
Yes. So you have.
I mean, I'm just scaling. I just want to.
This is surprising for many reasons. The first big surprise, at least to me, is that you get global solutions.
I understand.
Because so you have global in time.
Why? It's global in time. Yeah.
Jacek, if you go back to the previous slide, Jacek had constructed.
Global in
You
time.
see, T0 can be anything here.
Yes, no, I'm not controlling this. I'm just controlling in one direction the behavior.
Yeah,
Yes.
so
You're only controlling the negative direction.
Yes.
Yeah.
So.
But your solution, your thing there can. So you concentrate. I'm confused by the statement.
Okay.
I
So
want to see you constructed a concentrating bubble, right?
in minus infinity, yes. At minus infinity.
And you don't know what happens at T0.
Yes, here I didn't know. So for when this theorem was proved,
In the other cases, you're looking forward in time.
in both directions. So we know in what happens in both directions. So as a consequence, I had this in this remark here that the two bubble solutions from theorem 1 scatter in forward time, as a consequence of this theorem. Because here I couldn't tell. I didn't know what happens for positive times. I only had concentration for negative times. I knew that this solution exists for until some finite time, but I didn't even know if it blows up or not. So
these are not blow-up solutions. Right?
No.
I mean, is that correct? Or
no, they exist globally. So t minus is minus infinity, t plus is plus.
As t lambda t goes to 0, but that means as t goes to infinity, I suppose. Right? Yeah. Correct.
Yes. As t goes to minus infinity.
Or as t goes to minus infinity.
Yes. I mean, it depends here. I didn't write because it depends. It's stated like this: scatters in one time direction, in the other time direction. So I don't know in which. It can be in either this or that. Yes.
In the other direction, you have concentration.
Yes.
Some kind of concentration. Is that correct? You're asymptotically. You don't blow up in finite time.
No.
You just start to become more and more concentrated as time.
In one time direction, the other time there is scattering. Yes. Okay. Okay, so this is the concentration rate which we determine here what it has to be. Of course, this is the same as in the paper about construction, and exponential rate of concentration for k equal to 2, which was not covered in the construction paper. Okay, so this is what I mentioned, that we proved that these theorems which we know they exist, and now we know how they behave in the other time direction. They scatter, and this is what Dukertz and Merck calls reconnection phenomenon, connecting different types of behavior for a dynamical system. So scattering is a large open set. These solutions which concentrate are expected to be very special solutions. So we have kind of not a homoclinic orbit, but it's a very kind of a very special orbit from the dynamical point of view.
Yeah, but let me say, if you just go back to the main theorem again, I'll make sure I understand. So this is a global statement, right? I mean, this for any
In
No.
itself, it could be that theorem if they had just proved that t plus minus are infinite, t minus is minus infinite, t plus is infinite. That would have been a standalone theorem. It is completely unclear why at energy 8 pi k you should have a global solution always.
That's the statement. In
That's the
particular,
first thing. That in and of itself is a theorem. but they were able to
And
go
then,
much
in
further.
addition, then they
And-
classify the structure.
And either you scatter in both directions,
Or in one
nothing
direction you
happens.
scatter, in another direction you form these
And it's-
kind of solitonic
It
structures.
is remarkable that, for example, why don't you have two bubbles in both directions? You cannot have that. Either you scatter at minus infinity,
Yeah.
and then you form these two bubbles.
Yeah, yeah.
So you see a lot of information here.
Yeah, a lot of information.
Okay, so this is under this condition. Okay, this is a condition.
And the lambda of t has to be like that.
Yes,
So there
yes.
is even more information in that theorem.
Okay.
There
Yes.
You get this algebraic rate for lambda of t.
Yes.
Where,
Yes.
where is that? Sorry.
Top line.
Here,
we
yeah.
obtain
The lambda t. And that
That is the rate.
that means as you go to infinity, this is the rate at which you concentrate.
That's the rate that you get in the
Scattering direction.
Yeah, yeah, yeah. I
Mhm.
understand.
Okay. All right. So this is this.
And the scattering direction, you have that too, or?
Well, you just scatter, so you don't.
Scatter.
You
So
go
when you're
away.
scattering,
You are
you're
far
scattering.
away from the far away from the sum of two bubbles. So you lambda and mu don't make sense. Not make sense anymore. Okay. Yes. So this is we have mentioned a second ago that this is a problem which is quite, I would say, quite classical. Maybe it's too much to say this, but how of the collision problem of solitons. That for non-integral models they seem to not collide in an elastic way. So here, if we had two bubbles in both time directions, this would be like an elastic collision. They pass through each other and they form again a two bubble. This would what we.
Integral structure, but then you can have all kinds of other things happening in radiation, and other bubbles could be formed.
Yes. So here we don't have this, and so we proved that this elastic type of behavior, at least at this threshold case, is not possible for this equation. Okay. So this is an almost complete classification. It's almost complete because, in fact, we conjecture that there is, up to rescaling and sign change, only one solution which does not scatter. So that there is a whole big set of scattering solutions, just essentially one trajectory which is on the border of this region, which is a non-scattering solution. So in the phase space, when you imagine the ball of energy at less than 8k pi, and sorry, what? Yeah, the no, the bigger. So sorry, the region of energy bigger than k pi, and then the scattering region. No, sorry. No, sorry. The non-scattering region and the ball of smaller than 8k pi. Then the intersection is essentially just one trajectory. But this is not proved yet. Okay. So I would like to. I go until 10 to 12. Or 10. Okay. So about the proof, something about the proof, because I want us to see this attractive interaction, how it works. So I will talk about one part of the proof. So the proof of this theorem. The proof of this theorem involves two almost separate parts. One is kind of Koenig-Merz style concentration compactness analysis. In the spirit of their paper, earlier paper. And another part of the proof is what's so-called modulation analysis, modulation method. And I will talk only about this here. I will mention briefly what the second part is about. Okay, so here the game is to understand evolution of solutions which are close to a two bubbles. So we want to take any solution which has energy 8k pi and which is close to a two bubble configuration. Okay, so the distance for some u and lambda, the distance from a superposition of two bubbles is small, and the ratio of the scales is small. Okay.
Is lambda and mu constant, or are they time dependent?
No, here we have inf. Sorry.
Yeah, but they're not time dependent.
Okay, so here they are. So for any t, such that.
Yeah. Okay. So that's a mu of t and lambda of t. No.
No. So for each t, this is for each t. Yeah.
Ah, for you frozen t. Now you find
frozen t and.
Infinite-dimensional phase space.
Yeah. Okay. So implicitly your mu will depend upon time. Of course.
Okay. So here, in fact, I'm doing local analysis for a small time. I will do at first for short time.
I forgot your freezing your time here.
So here, if it holds at some time, then it will hold for a time which are close by continuity of the flow.
Yeah.
And I'm just trying to write some differential equations on this short interval. So, I mean, I need just some short open interval where the solution is closer to bubble. And I want to understand.
Why do you have this extra term lambda over mu?
Yes, because if the lambda is not much smaller than mu, this does. I would get something. Let's say lambda 1/2 minus so q 1/2 minus q.
Penalization term. You penalize configurations in which lambda mu are comparable. You build into this metric. Think of it as a metric in phase space. It measures the distance to a two-bubble configuration.
So you want them to be. You want the ratio to be small.
Because the theorem gives you that. So this is the metric that you use to prove
Okay.
it.
So here, for instance, q 1/2 minus q is not really a special configuration. I cannot understand how it evolves. There's such a data. I need really well separated bubbles, and then I can understand something. So how do I do this?
You're going to have to prove they're well separated, or they're scatter, right?
No, so here I assume. Okay, yes, later in the proof. Here, this is a part of the proof when I want to understand some part, the main term of the evolution, where I'm close to such a two-bubble configuration. Yes. So I'm trying. Okay, so we decompose like this: u of t as the sum of the superposition of these bubbles plus g of t, which is some function. I might sometimes call it the error term. And let's just compute something. We don't specify how mu and lambda are chosen. We will find out from the proof.
For us to understand, is it fair to say that this is a perturbative analysis about two-bubble configurations with radically different schemes? That's what you mean by modulation method? Orthogonality conditions, of course.
Yes. I would call this that. So.
Tom, right? So it's like a perturbative analysis.
Okay.
But you build in that lambda mu have to be very different scales.
Yeah, I understand. Yeah.
Yes, for maybe for more common.
You're building in that lambda has to be small with respect to mu, right?
It's small.
Either
You don't
lambda
care.
is huge and mu is 1 or
Yes. So maybe for more common multi-soliton situations, this will be trying to understand the dynamics of the centers of each soliton and speeds of each soliton. So we're trying to reduce. I think the physicists call it like this, also the modulation. That we try to reduce a model which is non-integrable. We cannot write in formulas the solution for this. But we are trying to reduce this to an ODE, to a dynamical system of finite number of real parameters, which is integrable. So more precisely to a finite number, to a set of differential inequalities, because we have to take the error into account. But
like a Laplace-Schmidt.
so yes, so this is what they call modulation method. Okay, so to show you how it works, I need some notation. There's the capital lambda v. I need the generators of the change of scale. So lambda 0 v is for the L2 scaling, the generator. And then this is, of course, the linearist operator, L lambda, linearization of the nonlinearity, the minus nonlinearity around u equal q lambda. Okay, this is a linear product. And so here what is important in the directive from the fact that we have this family of solutions, just by differentiating with respect to lambda, we obtain this. The kernel, we have an element of the kernel which is given by the generator of the scaling applied to q lambda. So this is no magic. This has to be always like this. Each time we want to perform such kind of analysis, we have some symmetry of the flow. Differentiating with respect to the symmetry, we have some kernel. Okay, and the error term, I just write the evolution of the error term. So I denote, to make it a bit shorter, the nonlinearity small f of u. And then just by straightforward computation, I obtain this, the dt of g dot. Okay, the g dot is not the time derivative of g, sorry. So the g dot is just a pair of functions here.
Yeah.
And we obtain this. And I forget some quadratic terms. I forget here. I kept just a linear part here.
Okay. But why? Because the other terms are going to be going to 0, or?
So first I'm trying to understand what seems to be the main order. Okay, so here I get this evolution term, and now it seems we want to, well, we want to compute anything. We want to prove that control any parameter, find some parameter which has some which is affected by the interaction. So here we compute the time derivative of this object, and this is because this is the in the kernel of the adjoint operator of the linear which gives the linear part. Okay, so here in general, because I also want to say that this modulation method is not specific. There is nothing specific about this equation is modulation analysis, because this is just saying that. Okay, so here this is a pair of functions. I'm looking at on the evolution of the pair of functions g dot. And the linear part of this would be given by the matrix 0, 1 minus L lambda 0 g dot plus etc. And I'm just saying that 0, let's call this operator T lambda, that 0 lambda q lambda is in the kernel of the adjoint operator T lambda star. And if we take any equation, the structure will be exactly the same. So there will be something in the kernel of the adjoint operator. Oh, sorry, where am I? Yes, here. And so I'm computing the time derivative of the inner product of the kernel of the adjoint operator with the pair, with the element g dot. Okay. So up to where am I? Yes, sorry. Yes, here.
Can you remind us what G is? I forgot what.
G is this, the error term. So U is a sum of, yes.
And then
is G going to be radiating, or I mean, is that going to be going to 0 somehow, or?
Yes, it will converge to 0. Yes. Okay. And we
why is dt G dot dt squared U? Because G is U minus the bubbles. Yeah. Yeah. I don't know. G dot is UT.
Is U DTU, yes. G dot is DTU. It's not DTG. Yes.
You don't have the bubbles in the dot term. Okay.
Yes. Oh.
Okay.
Yeah. All right. So this is what we obtain. This is where this is an explicit computation which gives this term. So this term gives this term. And now I have some. Here I get 0 from this, and here I have quadratic terms which I put here. So now the question is, and this is specific for the model. So this computation is not specific. What is specific is that we can get a bound from G on GT square, just from the conservation of energy. Because I'm looking at solutions which have energy 8k pi. When I do a Taylor expansion of the energy, this is a computation of the Taylor expansion of second order. This is what I get. But this is here, when I plug this into here, this is useless because this gives the same order of magnitude. So this is not enough, and what is enough to do is to add a small correction, which is small. So this is a quadratic correction. This is what I was computing before, the linear term. And then it's a quadratic correction, which is, okay, some localization.
So linear stuff doesn't do anything good. You got to add a piece of the anomaly there.
So almost formally, it gives you the correct answer, but you cannot finish the estimates just with this.
So you need a little piece of the nonlinearity.
Yes, you need to correct slightly. So this turns out to be negligible in terms of size, but in terms of time derivatives, this is significant. So this is okay. And with this, we can obtain this information. So we can obtain that the time derivative is larger than some constant, which is almost we need to make it a little bit smaller, but this is not so relevant. The important thing that we obtain that there is no more error term in this inequality. So I would say now I finished the modulation analysis because I had this evolution equation for the error term, and I obtained a finite dimensional differential inequality, which gives a non-trivial information, which gives me the growth of B. Okay, so now what I need to do is to relate lambda and B. This is a standard way, so I have not precised yet how lambda is chosen. it is usually chosen using some orthogonality condition. So we can assume that. So this is the way we choose lambda. We say that we'll choose lambda such that this is verified. That g of t is orthogonal to lambda q lambda. And by differentiating this condition, it is easy to obtain that lambda prime is essentially b up to some constant term.
So, you say you choose lambda, so you're choosing g, so it's orthogonal. You're not choosing lambda because lambda is chosen by your minimization procedure.
No, I'm choosing lambda because I'm looking at the solution. So for me, u is given. U is given by the evolution. This is the evolution of the wave map equation. And now I want to decompose u in some specific way, and so I choose mu and lambda somehow. And this is how I choose.
Such that when you wrote it down, it was chosen by minimization, that minimization condition.
No. So okay. So this is not the. So this is lambda of t now. Okay. So this is not the same here. Okay. Yes. Okay. So this lambda of t is not the lambda which minimizes the distance.
So that's just what, an initial approximation or something, or what?
Okay, so this lambda is not, it does not necessarily minimize the distance, but one can see that up to a constant this minimizes. So maybe you lose, you lose a little bit instead of being the minimum of the distance. Maybe you get twice the minimum, but
so that's just an approximation.
Yes. So it's just as good, let's say. It's just as good as a minimizer. It does not differ much from the minimizer. It doesn't have to be exactly the minimizer, but by using the implicit function theorem and some standard techniques, it can be shown that it's almost the same as a minimizer. So this is not the minimizer, but because the minimizer would not be convenient for the evolution of the for the study of the dynamical system. This is the guy who is convenient for the study of the dynamical system. So
that sets your lambda, does it?
This defines my lambda. Yes.
But the g is also defined in terms of lambda, is it or not?
Yeah, exactly. So g.
So there's a g that depends upon lambda and the lambda itself, and that condition.
Yes. So here I showed you in the order where if you gave me an equation and you told me to study this equation, this is what I would do. I would write the evolution for the error term. I would try to find the element in the kernel of the adjoint operator.
Okay.
And then once I identify this guy, I try to find the orthogonality condition, which so this gives me essentially what corresponds to the momentum in the dynamical system. So the B is what would correspond to momentum. And once I identify the momentum, I would look for orthogonality conditions which relates the derivative of the position to the momentum. So this is, I think that the easy. I mean, I don't have a the general framework, but for any given model, this is how it can be done. Okay. And the crucial thing is that we can actually deduce some information from these two. This is a set of differential inequalities which can be not exactly solved, but solved with sufficiently big precision to obtain, in particular, rates of concentration from this set of differential inequalities. So the way we do this here is that this is a 2D ODE. So we need the initial conditions, and how this ODE behaves is that when lambda prime is 0 at some point, t naught, so let's say typically it will attain its minimal value, then its evolution is controlled in both directions. So this tells us something about evolution of any solution which is closer to bubble, not necessarily the special one which was constructed. So what typically happens is that a solution can approach the superposition of q lambda minus q mu. At some point, lambda will have the minimal value. So there will be a focusing region. So for some time interval, it would be focusing. For some time, lambda attains its minimal value, and then it defocuses again. And in both directions, it does it at a specific rate, which is given by the solution of these differential inequalities. So this is this is where the modulation analysis stops, because there is no more error term. We just obtained that we computed the interactions at main term, and these interactions drive the evolution I mean, exactly drive what is happening. Okay, so I guess I wanted to show you how this is used in both theorems, but let me just say in 1 minute how it works. So as I said, the solution can approach two-bubble configuration, then defocuses again. So what we do is we take a sequence of solutions such that the initial data is a concentrated bubble plus this stationary bubble. And then we know that it defocuses in both time directions. But we take this sequence of solutions, so we start with a more and more concentrated bubble plus the stationary bubble. So for each element of the sequence, it has this behavior. It is not what we are looking for. It scatters in both time directions. It defocuses and probably scatters. But then we pass to a limit. And when we pass to a limit, what we obtain is a solution which never stops concentrating and gives this, and never scatters.
Never scatters.
Yeah, never scatters, because it just continues this behavior for infinite concentration after passage to a limit. Okay, so I guess I will maybe stop here. And